Now that we have the sound on. So if you missed the first little bit of this, you have to go talk to any volunteers. All right. No, I'm just kidding. Yeah, you have to find someone for the first part because I don't have a video for that. But here we go. Increasing and decreasing functions. The idea is that we say that a function's increasing if it's going up from left to right as the x value is increasing. And we say it's decreasing if it goes down from left to right. So here, what we're going to look at this graph, we're going to find out where are the slopes equal to 0. We're going to label where things are increasing in blue and where things are decreasing in red. So first of all, on this graph, it's quite easy to see that our tangents are going to be flat at that local maximum and that local minimum. Going from left to right, our function is increasing right here. So all of these points, f prime of x, is greater than 0. And if you wanted to check that, you could pick a specific point, draw a tangent line, and say, is that slope positive? Yes. Then between our maximum and minimum in this case, our function is now going down. And so it's decreasing. And again, if you wanted to check that, you could take any point, draw a tangent, and sure enough, the tangent on that line, the slope, is less than 0. And finally, after that, it would be increasing again. So any tangent line on the graph where it's increasing, which we saw when we drew that, has a positive slope or a positive gradient. So that means your derivative will be positive. And anywhere where you draw a tangent where it's decreasing, it's going to have a negative slope, a negative gradient. And we drew that as well with the red line. What we call any point where the derivative is equal to 0, we call that a stationary point. And in order to graph any function, there are some critical points. Those critical points include all of our stationary points and also all the points where your function is undefined. So if you're like having to divide by 0, that will become a critical point. We use these critical numbers to figure out where things increase, decrease, and where they're equal to 0. So what we're going to do in a bunch of these graphs is figure out where things are increasing and decreasing. And I've already pointed out the idea of that critical numbers, that you did them with inequalities in the past. And that's just a little note saying, remember when you did that? And you've checked each section where it was true and false? It's kind of that same idea with calculus. So we're going to do a couple of examples here that are really going to see that. So we've got a graph. We know this is a parabola. We know it has a vertex. But instead of completing the square like we used to, we're going to find that vertex, that critical point, stationary point, by taking the derivative. The derivative is just 4x plus 1. And if you set that equal to 0 to say, when is my tangent flat? When is it horizontal? Solving for x, you're going to get -1/4. If you plug in -1/4 in for x to see what y will be, you will get I don't know. Someone want to check that? You plug it into the original because this would be a point on your graph. So that's a good question because there's going to be lots of times you're going to plug points into the derivative. Sometimes you plug points into the original. The question you have to ask yourself, am I trying to find something on my graph or am I trying to find something where it's increasing or decreasing? Because if I'm trying to find out something about the slopes, increasing, decreasing, then I'm going to plug things into my derivative. If I'm going to try to find a specific point that's on my graph, then I'll always plug back into my original. Anybody check that value? It's right? Okay, good. So now we have a stationary point, and what we're going to want to find out, is there any other critical points? Is there any non-permissible values in a parabola? Anytime you divide by 0? No. So when we go to our sign diagram here, the only point we have to put on is -1/4. What happens to our slopes before -1/4? So you plug in a number before -1/4, like -3. And now we're plugging into the derivative because we want to know about the slopes. If I plug in -3, it's pretty obvious to see that it's going to be negative. So I'll put a little negative sign here and I'll draw an arrow because I know that my slopes are negative. That means our function is decreasing. And after -1/4, plug in 10. Pretty obvious that when you plug that into your derivative, you'll get a positive number. So afterwards, it's going to be increasing. No. We'll look at some where they go increasing, increasing. But this is a parabola. So you already knew, once you found this vertex way down here, -1/4, -21.125, once you found that and you knew that the 2 was positive, you knew your parabola was going up like this, okay? Because of your previous knowledge about parabolas. Now our calculus has shown us the same thing. As we move from left to right, can you see that it's going down to a vertex and then up afterwards? So this is just showing how the calculus shows us that now and how we used to do this. If you're graphing things by calculus, you'll have to show that work. Okay? What we're going to move to, this is another parabola. I'm going to leave this one for you to do maybe at the end of class. We're going to skip this one right now because it's just more of the same. But let's start to look at some of the other types of graphing that you may have forgotten, like 1/x². You learned a whole bunch of techniques in grade 11 and 12 for reciprocal graphing. You may have forgotten those by now. So now how can we use calculus to do the same thing here? Again, what we're going to do is we're going to take the derivative of this. First of all, I'm going to write this as x equals -2. Solving that for the derivative, the -2 would come out in front, subtract 1 from the exponent, and just so we're dealing with things with positive exponents, I'm going to rewrite that as -2/x³. Is this ever equal to 0? No. It's never equal to 0. Some things that are important to know. If a fraction is equal to 0, the only way a fraction can equal 0 is if the numerator is equal to 0. The numerator is the -2. Is -2 ever equal to 0? No. In fact, if you were trying to solve this, one of your strategies for solving an equation that has a fraction is to multiply to get rid of the fraction, right? So what happens if you multiply both sides by x³? Right? Multiply both sides by x³ and you'd get 0 equals -2. And you're kind of like, is that true? No, it's a problem. And anytime you come up with a major contradiction like this in a math problem, either it means you made a mistake earlier and you got to go check your work, or it means that there is no solution. And that's the case here. This never works. It never equals 0. So when we go to do our sign diagram, we included all of our stationary points where it was equal to 0, but there are none. The other thing it said to include was all points where you have non-permissible values. Do we have any non-permissible values in our original graph? Yes. Right? X can't equal 0. So we will put 0, because it's a non-permissible value, on our sign diagram. To figure out if this is increasing or decreasing, and this will answer your question from before. Well, no, this one will still switch up. But if you try something less than 0, and you plug it into your derivative, which is negative 2 over x cubed. So if you plug in a negative number, can you see that a negative number cubed will still be negative, and a negative divided by a negative will be positive? Again, I'm not concerned about what the actual answer is when I plug in negative 2 or negative 3. I just want to know if it's positive or negative. And because of that, I know my graph is increasing. After 0, if you plug in a positive number, while the top of our fraction is negative 2, the bottom will be a positive number. A negative divided by a positive will be negative. It's going to be decreasing after. So our calculus is telling us that it's increasing and then decreasing. Something that we do have to still use when graphing all of our things using calculus, we still have to use our knowledge about asymptotes. So in this graph, because we have a non-permissible value at x equals 0, what does that mean? There's going to be a vertical asymptote right here at x equals 0. We can use what we know about limits to find our horizontal asymptotes. So now, what happens as x goes to infinity for this? What does it get close to? It gets close to 0. So we're going to have a horizontal asymptote at y equals 0. So when x is less than 0, and using our knowledge of asymptotes, you have two possibilities here. You have the possibility that your graph looks like this or like this. Which is the only one that's increasing? The top one. So we draw the top one. Then in the next stage, you could have it look like this or it look like this. Which is the only one that's decreasing? The top one. And so we end up with that graph. Do you remember your techniques for learning how to graph this using the reciprocal? You may have learned to first draw your parabola. Then wherever you had x-intercepts, you drew vertical asymptotes. Then you learned that if your graph went up forever or down forever, got bigger or bigger, either positively or negatively, you drew an asymptote at 0. Then you took some values. For example, if you had 2, 4, the reciprocal of that means you have 2, 1 over 4. And this point where they both intersect is at 1, 1. And you did some points that way. So that's a little bit of how you did that graph in the past. But now we're looking at our critical points and seeing it's increasing, it's decreasing. We still had to know things about asymptotes in order to draw this. So let's do it with x cubed. X cubed is going to be very similar because when we take the derivative, and write it as a fraction there, again, this never equals 0. And if it never equals 0, there's going to be no stationary points, no little relative maximums, no relative minimums. Just like last time, though, we do have a non-permissible value. X can't equal 0. All right. So it's never equal to 0. Our sign diagram, we still have to put the non-permissible value on there, x equals 0. Now, this one's going to be interesting because when we pick a number less than 0, the bottom is x to the 4. X to the 4 is always positive, no matter if we put in a positive number or a negative number. So the bottom's always going to be positive. The top is negative 3. It's always going to be negative. And we have a negative number over a positive number. This is going to be negative. It's going down. After 0, it's also going to be negative, going down again. When we go to draw our graph, the first thing we're going to have to do is add our asymptotes. Because we have a non-permissible value at x equals 0. And if we look at the limit as x goes to infinity of 1 over x cubed, we see that we have an asymptote at y equals 0 as well. Now, what's the only way you can draw this so that it's going down in both sections? This part has to be above or below? Below. This part has to be above. The function is always decreasing, even though there's a big jump after that asymptote when it goes from huge negative numbers to huge positive numbers. But the function itself is always decreasing. So we can see how calculus can help us draw these graphs that we did before with our reciprocal. It can also help us draw these graphs that you did with x to the 4. F prime of x. And the nice thing about the calculus technique is the technique is the same whether you're doing a parabola, an x to the 4 graph, a reciprocal graph. So whereas in the past you were learning all these different techniques for different kinds of graphs, which is good because each individual technique sometimes is the shortest way to graph that function. But it's nice to have one overall technique that can do everything. And that's what the curve sketching with calculus does. You start off with your derivative. Your derivative in this case, 4x cubed minus 16x. Set that equal to 0 to find out if you have any stationary points, which are your relative minimums and your relative maximums, because if your slope is 0, your tangent is horizontal. Can you see that you can factor out of 4x? Whoops, 4x. So factoring it completely, we find out that there's 3 places at x equals 0, at x equals 2, and at x equals minus 2 that you're going to have either maximums or minimums. I'm going to figure out where these points are on my original graph. What happens when you plug in 0? What point will that be on my original graph? 0 minus 3, minus 3. So I when I want to find an actual point on my graph, I have to plug it back into my actual equation. So I plug 0 into my actual equation to find out what that point was. If I want to find out what happens with 2, 2 to the 4 is 16, minus 32 is negative 16, minus 3, negative 19. Can you see that plugging in minus 2 will give us the same answer? Because whether it's the power 4 or the power 2, it'll become positive. So this will be minus 19 as well. As far as our sign diagram goes, and I'll start calling this what we're going to call it later. What we're doing right now is called the first derivative test. The first derivative test tells us where things are increasing and decreasing. And because of that, it's going to tell us whether these 3 points are maximums or minimums or something else. So in this case, negative 2 on our number line would be there, 0 there, 2 there. If you try something less than negative 2, okay? And when trying something less than negative 2, we could plug it into this equation to find out if it's positive or negative. But we're going to find it's a lot easier to plug things into a factored equation than it is to plug it into a regular equation. Why? Because if I plug in something less than negative 2, like a negative 5, I can tell right away that this is going to be negative as my first factor. And I plug in negative 5 here, I know this is going to be negative. And when I plug in negative 5 in this one, I know this is going to be negative. A negative times a negative times a negative is still negative, so I know this section is decreasing. When I try something between negative 2 and 0, like negative 1, can you see the first one still negative? And negative 1 minus negative 2 is still negative. But in our third one, negative 1 plus 2, now this one is positive. And if you did a negative times a positive, you would find out that this section is positive, and it's increasing. That already tells us that at minus 2, this is going to be a local min. Because if it's going down and then up after, the only way that can happen is if that value is at minus 2, is a minimum. Now what happens between 0 and 1? I mean 0 and 2. Let's say we choose 1. Plugging in 1 here, this is positive now. 1 minus 2 is negative 1. This stays negative, and 1 plus 2 is 3. This stays positive. Positive times positive. And now this section is negative, and it's going down again. So we now know this point here is going to be a relative maximum. And of course, after negative 2, when you try 6 billion, positive, 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 it's going to be going up after that. So now when we go to sketch this graph, we have some very powerful information. We know some key points. We know at 2, negative 19, negative 2, negative 19, and 0, negative 3, are 3 points on our graph, and they're key points. We know that our function has to be decreasing left to right, so it's got to go down to this point, bottom out, then maximum, then minimum, then increasing again. So our first derivative test says it goes down to a minimum, then back up, then down again, then back up again. In grade 12, you graphed x to the 4 graphs. You learned about multiplicity of zeros. You tried to find your x-intercepts and then graph it. What you learned about an x to the 4 graph is that a positive x to the 4 graph acted like a parabola but might have some bubbles in the middle. Sometimes it did, sometimes it didn't. A negative x to the 4 graph looked like that. You found x-intercepts, and then you graphed it through those points, but that's all you could do. You could find x-intercepts and y-intercepts. And you could only find x-intercepts if it factored nicely. So for this graph, if we tried to use what we learned in grade 12, the first thing we would find is we can't factor this. We can't factor it nicely. So we wouldn't be able to find our x-intercepts. We could find our y-intercept and be happy about that. And we would know that the graph looked something like a parabola, that it would be coming from down here and ending up over there, but that would be the extent of it. And we wouldn't be able to add any more information. Now with the calculus, these key points, these maximums and minimums, and where it's increasing and decreasing, we've got a really quite accurate graph at this point. We still don't know our x-intercepts. We'd probably have to use our graphing calculator to find them. But we've got quite a powerful set of answers right now. And quite an accurate graph. So we're going to take the last 15 minutes to practice these.